Okay, hi, I am Biniyam, and I'll be presenting about our project for the duration of Spring 2024, which is leveraging large language models to solve tasks in virtual environments. Here's the table of contents. So let me give you a brief introduction. Recently, advancements in the field of language models have enabled remarkable results in language understanding and predictive reasoning. The size of the language models have been increasing steadily, and the same goes for the performances. In fact, as you can see in the second plot, some language models now surpass human baselines in these tasks like predictive reasoning. In addition to significant advances in natural language processing, large language models now integrate additional modalities such as vision and time series data to create multimodal LLMs. These models excel in tasks like contextual understanding, reasoning, and scene recognition. A general architecture involves having a common embedding space for these different modalities, allowing for information to be efficiently learned from these different modalities. By leveraging diverse data sources, multimodal language models can process information more comprehensively, resulting in a more accurate prediction and effective solutions for complex tasks. Among the most well-known tests for artificial intelligence are the Turing test and the Hofstadter test. The Turing test, devised by Alan Turing in the 1950s, posits that a machine can be considered intelligent if it can engage in a conversation with a human without the human realizing that they're talking to a machine. In the paper, Does GPT Pass the Turing Test? The authors evaluated GPT-4 in a large-scale public online Turing test. They found out that GPT-4 was able to convince human evaluators that it was human around 49% of the time across different tests. The Hofstadter Turing test, proposed by Douglas Hofstadter in 1982, states that an entity passes the test if it creates virtual reality, and then a computer program within that reality recognizes itself as an entity and itself passes the Hofstadter test, therefore creating a circular challenge that has yet to be achieved by any human. Inspired by the Hofstadter test, in this project, we evaluate the performance of large language models in virtual environments. So far, we have been working on creating a virtual environment where a character can interact with and solve tasks using the processing capabilities of multimodal LLMs. In the first phase of our experiment, we attempted to use the text modality of language models, specifically GPT 3.5, to solve tasks in a virtual environment. Initially, we utilized the virtual world simulation engine called Roblox to create a character and environment for solving the Tower of Hanoi task. Then we sent the current state of the environment to the LLM and utilized the response to enable the character to solve the Tower of Hanoi task. We developed custom functions to translate the state of the current environment into text for the LLM. Additionally, we implemented action functions to convert the LLM's responses into executable commands. Here's a demo of our first phase. So as you can see here, the agent gets input from the environment, sends it to LLM, and executes the actions inside the virtual environment. We extended this first phase to include solving Rubik's Cube. However, due to the high amount of sequential reasoning required, the performance of the LLMs was not satisfactory, with a success rate of around 10%. This poor performance can be attributed to the degradation of LLM's capabilities as the context length increases. In the second phase, we extracted visual information from the scene using the agent's first-person view camera and transferred both the visual and textual description of the current scene to the LLM. To enable this functionality, we transitioned to the Godot framework. The selected task for this phase is assembling a table from its parts. After receiving a response from the LLM, we parse the result and perform the actions using the agent. Here's a demo of the second phase. So as you can see here, the agent walks to the table, uses the parts, and by getting responses from the LLM, it assembles the right parts to the right place. The camera on the left is the first-person view from the character. So as highlighted in the chain of thoughts paper, large language models tend to produce better results when prompted to reason through their responses. We implemented a prompting method that was inspired by this approach, called the program of thoughts, to generate answers using a predefined set of functions in the provided programming languages. Preliminary results indicate performance improvements, although the analysis is still ongoing. By incorporating ideas from chain of thoughts prompting and program of thought prompting, we observed significant enhancements in performance. However, the implementation of these techniques posed certain challenges, which we are addressing right now as we refine our methods. One limitation of LLMs is hallucination, where the model sometimes fail to generate realistic answers and may produce out-of-context responses. Another challenge is handling longer sequences. As the input and output length increases, such as having more disks on the Tower of Hanoi tasks, the error rate of LLMs rises. This issue discussed in the Lost in the Middle paper highlights the difficulty of LLMs mainly in maintaining context over long sequences. To mitigate these problems, we implemented several approaches. First is conducting multiple runs and selecting the most frequent answer to ensure the LLMs produce the correct responses. And the second one is experimenting with additional textual input for scene descriptions to enhance the understanding of details in the image inputs. So future directions, one is completing the implementation of the phase 2, and second one is exploring the capability of LLMs in scene recognition, as there are many interesting works coming out like the scene LLM paper. So yeah, thank you for listening. This was my presentation.
Thank you very much for your presentation.